Okay, so yeah, let's get started. Let's go to Firefox. Here's the we worked on the given we discretized the action space so that rather than continuous all possible angles to launch something from, we kind of I just arbitrarily chose the number eight as like eight cardinal directions. Well, yeah, to launch. So given the move indices from 0 all the way to 7, these indices essentially specify a direction. The move IDs are from 0 to the number of directions minus 1, so 0 to 7. That's 8 directions, the indices. And then we create a function that given the number does some trigonometry to get the actual velocity components that we desire. And remember that the y component is actually negated. Like we flip its sign value, we multiply it by -1 because the axis because in the game coordinates everything is measured from the top left corner, not the bottom left, as is traditionally like the case in like the origin for math, but everything is top left. That means as you go down, y actually increases. So anyways, so that's like the main like the minor wrinkle, but otherwise everything's pretty obvious. So let's get started. So one thing I was thinking of doing is you know how I had some changes. Okay, so first of all, I actually scrolled up. I'm gonna start a new terminal. But what I just want to do is I want to copy this, and I believe I did like a git restore instead of a git stash. So actually, I was thinking of kind of creating like a new test file, just where I can kind of do these things. Because last time I kind of wrote some code on net.ts just to print out a bunch of stuff like these consoles, just to show this kind of function right here, which I did yesterday or whenever I last streamed, net.getMoveVelocity from movedir. I just talked about this. We tested out this function. It's pretty much correct, so that's good. But the way we tested it is we added we did some kind of work on net.ts, which I kind of comment or did and then kind of cleared out. So I think rather than kind of contaminating our net.ts file and polluting it and kind of undoing it, I think it's better to just kind of move this on a test file. I did something similar for prior projects, like fixed point two. So let me just copy this. I'm going to quit the terminal. And I'm going to let's see yeah, so open a new terminal, right? And I want to just kind of go into fixedpoint.ts or fixedpoint.js, and if you look at kind of this project, I have something called a scratch, or I guess test fixed point, and then scratchpad. Okay, so I think scratchpad, like test. Okay, let me actually look at the repository right on GitHub. BumperCoins, like kind of fixedpoint.js. So if you look here, you see test fixed point and fixed point, like the fixed point files, but notice that you don't see any scratchpad, right? Because if you look at the git ignore, right, then I'm actually specifically ignoring the scratchpad.ts. So scratchpad, if I kind of do cat scratchpad.ts, is I kind of okay, so I'm kind of having some test data, and then I'm just kind of yeah, just working printing it out and kind of I guess doing a mod operation. But yeah, I'm testing stuff that ends in point 0.5 or ends in point 0 or something. But yeah, it's just a nice kind of way to just have a scratch pad. So I think I'll copy that convention or that kind of technique or concept where I'm just gonna go in my git ignore and kind of add scratchpad.ts and just kind of create that file and various if I want to fiddle with stuff and just kind of try stuff out, I might as well do it in the scratchpad as opposed to contaminating existing files. Okay, let's kind of go back to work, I guess. Its status. Okay, so everything's clear. I pushed it off screen. So now it's a v or let's kind of go to our git ignore. Git ignore. Let's kind of create a scratchpad.cs. Okay, that looks good. Git status. Git diff. Git at all. Great. So now let's create the scratchpad.cs file. And let's paste, oops. Oh, well, I guess I don't have it. Anyways, there's no point doing it right now because I already kind of like did it. So git status. And notice that like we don't see the new file because we added to ignore. We don't see scratchpad.ts even though we created it. So okay, that's good. So anyways, let's go back to net.ts. Let's kind of open a scratchpad too. Or actually, no, well, let's sorry about that. What? Net.ts. And let's look at connect4 for reference and then scratchpad. Okay, so right now we have well, let's go to connect4. So then we have the create model. We have our own neural net for so this connect4. But like we have this in BumperCoins. We have our own neural network. We have also done a convert game state to model input. And this thing right here, like I kind of skipped that and I did this, but I think we have to start off by working on this today. So right now, like we haven't done this yet, but we have done get policy and value. That's what we did. That's what we did past few streams. Get policy and value. Actually, and then there's a train model, which actually trains the model. So this one right here, which actually trains the model, so what does it need? So this stuff right here pretty much like relies, like we can copy this directly as long as like this thing works. Like it doesn't like, it's not assuming anything specific to connect4 here. It's just a general thing. So like we have a type, oh yeah, GG. We have this type example. So game state policy and number. In fact, I'm gonna copy these 2 lines. 3 lines, sorry. Good. So we have our example right here. And then we have train model. So right now, like we've basically finished left to right in theory, assuming our get policy and value is implemented correctly. Then what does that mean, right? Like, what does this mean, get policy and value? So what does that mean? That means like, well, technically symmetries, but once we do symmetries, finish symmetries, then we've kind of like, we're able to generate training data because like just Monte Carlo tree search, right? Like given a state, like well, let's say we kind of have a game state and then we want to like decide what a policy is for it. So we just do MCTS, right? Like we take the game state and we query its we take the network and we do a create node on it, right? Which creates like wraps that in an MC node. And then you know what we did for C4, like the Monte Carlo tree search. So like so create node would like kind of wrap it around, create a node, and like kind of take the game state and you know, just take the neural net and do a predict on it. It'll call get policy and value on it. It'll give us a value and a policy. So initially, the root one, we don't care about the value, but the policy does give us the weights for like, we create the MC edges from the policy, like weighted by the policy weights, the probabilities. So now, and then like, so, okay, so now we have an MC node and we have like all these edges. So then we use the UCB thing to like, and then like we recursively call search on it. So what search does, given a game state, given an MC node, is it just kind of like looks at the policy or it computes the UCB score, so then it selects the edge, the action, the move to make, which it greedily selects that with the highest UCB score, and then it drinks some well, let me finish this speech and then drink some coffee. But like, so we use greedy to like greedily like take the maximum arg max. We take the most promising edge or the one with the highest UCB score, and then we what do we do? So we choose the edge, and then there's two cases. If the edge has already been traversed, that means it has an MC node attached to it. Then we just recursively do it. But if it doesn't, then what? Well, then we what do we do? Yeah. So like then we like so if we have never traversed this edge before, that means it doesn't have an MC node. That means we have to actually call create node, and that's where this thing again gets used. First of all, we call it, and then so first of all we take our state, right? And then we clone it, and that's crucial. We have to clone it, which so that we don't destroy anything, and also for a back pointer, so we clone it, the state, and then we kind of like call apply move on the clone, and also pass in the thing that we cloned for the back pointer too, because of the historical stuff. We want a back pointer to the previous game state. So, anyways, so then like so we clone it so we don't like for immutability we don't want to like muck around and like mess up like we don't want to mutate the change the game state's values because apply move is a destructive operation, right? It updates the coin's coordinates and stuff, so it's a destructive operation. That's why we have to clone the game state, and then we call apply move on that, and then we get a new game state, the next one, which is the outcome of taking the action, traversing, taking the edge's move on it, right? So after we take the action, what happens, right? Like, what do we do now? Well, we so now we have a new game state, the next one, and then like create node just kind of like wraps that in an MC node, and then it calls like so we have like the next game state, and then we have to like call get policy and value. We have to basically take our neural net, we have to take our next game state, you have to call this function which gives you a policy and a value, and then from the value we're going to return the negative of the value and just back propagate that up as the MCTS search function like kind of recursively like goes down and propagates back up. As the recursion unwinds, we just kind of like propagate up we're returning the negative value, like just like the negamax, minimax algorithm, standard stuff. And we also and then so like we propagate the value and then like we return negative value to like recursively. And from the policy we kind of create new MC edges, right? With the weights being the policy probabilities. So right now we kind of have sufficient information to do MC search. The only thing is like rather than take the game state in the model, the only thing which we haven't taken account for is symmetries. So like given a game state, what actually happens at MC search is we don't like directly call the model on the game state. We instead like randomly select a symmetry, and then we kind of like use that symmetry and like we kind of like flip the game state horizontally or in Connect 4 or potentially vertically, which we can't do in Connect 4 due to gravity. So we have more symmetries in this game. Like in Connect 4 we have two symmetries. In this game I think we have four. And like because it's 15 by 20 and it's not like 15 by 15, it's not square. I don't think like I think we may have had more symmetries if it were a square thing. I'm not sure, but I know we have at least four. I'm thinking flip horizontally and flip vertically. So that's two symmetries. So that gives us like 2 times 2 is a 4. So we have like four combinations of them, like mixing and matching. So so then so yeah, so like we have to actually like the only difference is we have to kind of like do symmetries, but if we assume that there's no symmetries in just the game state itself, like when we kind of we have the next game state, we have to actually like kind of invoke some symmetry on it just to I guess that's just what we did for Connect 4 and like what the AlphaGo algorithm does, AlphaZero does. So we want to be consistent with that. So we have to just, but like, so right now we basically have enough like functionality, assuming this function's implemented correctly here. Well, no, this is Connect 4 actually, but like assuming we did it in the previous file for BumperCoins, then that means that like we have enough information, assuming I mean, to actually do Monte Carlo tree search and to actually generate training data. Now, again, we don't because we actually need to do a little bit of work for symmetries. But once that's done, then in theory, we have like the self-play down. Like we are able to like take the neural net and do Monte Carlo tree search policy improvements, right? So now we have a bunch of like, assuming symmetries is done, we'll have a bunch of training data. And now to actually train the model, let's see how it's done, right? I think we just copy this function. And the only thing we need is this function right here to be implemented. And then we're actually done. And symmetries too, because when we train, we also do data augmentation in the train.ts file, right? Because we want to like generate more, make it more like kind of robust and more generalized to the symmetries and stuff too. Just data augmentation. So let's recap training model. Actually, no, wait. Before I do it, before I recap this, let me just take a break and drink some coffee. Okay, so train model. So we have so its input, of course, we need the neural network, and then we have an array of examples. Again, example is the game state, the policy, and the value, and the value, which we are labeling. Like once the game finishes, we assign this like it can be +1, -1, or 0. And then we all know what that means. 0 means draw, +1 means player one, or +1 does not mean player one one. +1 means that whoever player the game state like is currently for, that player won, right? So that if it's the first game state, that means it's player one's true, and if the number is one, that means hey, player one won. But if it is the last game state and it's player one to move, and then it's +1. Wait, yeah, what happens then? Never mind, never mind. Anyways, but the point is that like we have a game state, and like +1, -1 is from the perspective of the game state that is for P1 or whatever like is P1's turn. So like whoever turn this game state is for, the +1 or -1 is from like the perspective of that player. So if player one wins the game, then we have a game state that is P2 turn, then like and -1 basically means that player one won, player two lost. And +1 would mean that player two won. And like it's from the perspective of the game state's current player, right? It's not from the waiting player, but the player whose turn it is. Not the player who's waiting. When I say waiting, I mean like waiting for the other guy to make a move. So the current person is not waiting because he's the one actually in the driver's seat. So anyway, so we have like an array of examples, and then like, so what do we do? First of all, we get a number of examples. That's it. That it just kind of gives us the size of the other dimension, right? The outermost dimension, like NHW, like N. What's it called? Like kind of like NC or NHWC. So like we're getting the N, the number of like the batch, like the number of examples. That's like the N right there. That's that dimension. So we kind of get the size of it. And then we have the x's, the y1s, and the y2s. Like y1 and y2 are like either like policy or value, whatever, because you have two output heads and like one input head. These inputs. So what do we do? So first we get the number of examples, then we initialize these three arrays. And then again, like here's the actual fit. We kind of fit the x's with the y1s and y2s. So for each example, what do? We take we want to populate this. So after we iterate through all the examples, these would be populated and then we do the train. Well, we do some kind of TF things, operation. So X's array, we push the convert game state to model input, which we have actually just done and printed out the image stack. So this one we kind of do here, and then after that we concatenate all of them because right now like this array that like the thing that we're pushing is not like the actual image stack, but it's actually a wrapper around that. Like it's a singleton list. A singleton list as in like in a list which only has one array. I mean, sorry, which only has one element, the image stack, right? Like in here, what we're returning, right? Like after the transposition is like in Connect 4, it's like we have like our image stack, which is like the stack of these two images. But then like notice how there's two brackets. There's an extra outermost bracket. That's to get the n, right? It's kind of like that. So like because of that, that's why we're using tf.concat. I mentioned this at a prior stream. I was a bit shaky, unsure if I did it correctly. I just looked at the documentation, and from the documentation, the TensorFlow.js website, I kind of decided to use concat versus stack. It turned out my interpretation was absolutely correct, so I'm glad that worked. But that's why we're using concat. Concat basically kind of like it concatenates like whatever the dimensions are for the elements in the x's array, like those kind of get the same. Like you have a list of like 1 2 and a list of like 3 4, and you concat and you get like a list of 1 2 3 4. So like it's still like the same shape of the list. So concatenate kind of preserves the extra n, the extra wrapping dimension. So that's kind of why we're concatenating. Whereas for the y's, what we're doing is let's just look at the value one, right? The value, we just kind of like create like a singleton thing with a value. So again, the singleton thing is just to get the n, the number of examples dimension. And then what do? We just kind of stack it up, right? We just stack them because stack kind of like adds a dimension because like, wait, no, what am I talking about? No. This outer wrap that we're doing is not for the batch for the n. This outer wrap is just to is because that's just the value head, right? The value head is that's the shape, right? That's just the shape. So if you look at convert policy to texture and look at its shape, like this is just like a singleton list because the value is a singleton thing. Whereas the policy is what? Like the column size, number of columns is 7. Like a policy is like is a list with 7 elements. That's its shape. Like if you look here in convert policy, right? We kind of like get the policy data, which is like kind of we push num calls as 7 columns. So like we have a list of 7 elements, and we kind of like we just what do we do? Yeah, so like we just like take the proper index and like yeah, we just kind of correspondingly populate these things, and then we return the policy data, and we're also specifying the shape exactly. This is the shape. Just a list with 7 things. Like the value head only has a list with 1 thing, like a singleton list, whereas the policy head is not a singleton list, it's a list with 7 things, right? Just like for BumperCoins, there'll be a list with 2,400 things, I believe. So we just kind of convert that to a tensor, just like we kind of like wrap it to like create instantiate a tensor with a value head. But then these things are just like per example, but then we have to actually stack them together and create the n dimension, create the extra dimension. So that kind of explains like the stack. It changes the dimension size by like kind of adding a new dimension. So now we have the x's and then the y's and the y2's, and then everything kind of matches. Like the outermost dimension for all of these is the same. It's the n dimension, and what's its length? Num examples. So we just kind of like call model.fit. So that's good. So this assumes nothing for Connect 4 specifically, except like the only assumptions we're having are the shape of the neural network, basically, kind of. Or never mind. But the point is that like the shapes match for my thing, so I can just kind of copy this whole thing. So let's do that. Let's copy this. Let's paste it. And that is completely fine. The only thing now that's left to get this function to work, because again, I'm like right now I'm assuming that we're practically finished. Assuming we have symmetries done, then all we need, if we have symmetries done, I'm saying that like with this function here, and like with the game states apply move, we have sufficient logic to actually implement our Monte Carlo tree search. That means I can just like copy the mcts.ts file, make that change, which I mentioned earlier about cloning for the back pointers to pass it into apply move, the previous game state. And we have enough information or enough code, I think in theory, once symmetries is done, to actually do a full episode of self-play. We can actually play with ourselves, have our bot play against itself, and generate training data. So now once we have the training data, what do we have to do? To complete the loop, we just have to call train model, right, on the training data. Well, again, we need symmetries to do data augmentation, but like assuming symmetry is done, we just need to train the model, and then boom, we can do alpha 0. Like we can fulfill our feedback loop of generating training data using our net, and then taking the training data and using that to improve the net, taking a step in the better direction, improve the net, and with the improved net, we generate more training data, and then more training data improves the net, and it keeps going on and keep, in theory, increasing the gate playing strength, or hopefully. I don't know about theory, but hopefully we're done with alpha 0. So all we need now is to convert policy to tensor. So that's it. And symmetries. So that's what we're going to do. At least what we're going to do is at least do convert policy to tensor. I think that's an easy, a very kind of low-hanging fruit. So let's just do that. And then maybe call it a day, or call it a stream. So again, today's a pretty light day, I guess. Not really doing much. I feel like the closer I am to finishing something, the less motivated I get. Because again, the hard part was already done for Connect 4. So okay, now we have to, wait, what did I do? Yeah, I just paste this function. Let's just kind of save this. And now let's actually kind of wrap everything in comments, because because yeah, this is from Connect 4, so we just have to kind of do this. Like, we have to implement this. So okay, let policy data equal empty list. That's fair enough. And what are these lines doing? They're just like kind of pushing zeros. That is perfectly fine. So now let's kind of copy this but change it. So like, what's our policy head? Like num calls? No, it's something different. Like, what's our policy shape? If you look at the outputs, right? The policy output units are what? The number of moved ers, which is 8, times the rows times the columns, right? Which is 2400, right? 8 times 8 is the number of moved ers. Number of rows is 15. Number of columns is 20. So 15 times 20 is what? Like 15 times 2 is 30. So 15 times 20 is 300. Times 8, 300 times 8, 8 times 3 is 24. So 2400. So yeah, 2400. But let's not write 2400. Let's keep it in terms of all these variables, just for kind of generalize it, just stylistically. I don't want to hard code stuff. I want to keep it in terms of variables, like symbolic. So okay, so rather than kind of doing it from here, let's kind of like do that, or sorry, do this. Right? Okay. So now we have created kind of everything like of that, right? And we've created a zeroed out thing. So it's kind of like so now, and we have to change the shape too to make it correct. Now, one thing I could do is actually like take this kind of expression right here, like these three things multiplied together, and I could actually like compute them in the top, and I could kind of like just kind of like clean up the code by kind of, rather than like doing these three like this multiplication so many times in the neural network and twice here, I can just pre-compute it at the very top as like the output shape, and just kind of like recycle that. In fact, similar to like what we did last stream, right? Like we have like, sorry, the move direction on stuff, like get move velocity from move dir, right? I feel like it's actually better, rather than to compute this every single time, is instead we can just compute it all for all the 8 directions, and then this function will simply be a lookup actually. Like it would just yeah, we don't even have to like kind of do that. Like we can kind of like cache it and only compute it once for all the directions. Cause like this stuff should yeah, it feels kind of wasteful doing it every single time. Now, should I really make the change or not? Okay, I'll just put a to do, I guess. Actually, no, let me just do it right now. It's a low hanging fruit. So kind of create an array of that equals like this. And then For let I equals 0, I is less than what? Let's kind of go back to top. No movers. No movers. I plus plus. So for I is equal to 0, I is less than the number of movers, I plus plus, right? So this kind of like gets it. Then, or instead, not I, let's call it move ID. So from move ID is that, then what? Take all this stuff. So then what? Move velocities by mover dot push this stuff. Just like that, right? So in this thing, what we simply do here, now that we kind of have a pre-cached, pre-computed, is we return this thing, move velocities by mover of the move ID, right? Just like that. Okay, so now let me just like do a quick compile check, right? Make sure everything compiles. Because I did a bunch of changes. Okay, good, everything compiles. Okay, so that's good. Now let's just kind of go back onto, let's just go only onto net.ts for now, because I already kind of copied the connect for stuff. So okay, basically doing this convert policy to tensor should actually be like kind of basically the similar, like we have to use discretized coordinates. It's gonna basically be kind of like the inverse of get policy and value, right? Like it's gonna be quite similar. Like we have to do the same thing here. But anyway, so actually, yeah, let's just get started on doing that, right? So convert policy to tensor. Oh wait, this is actually wrong. Convert policy to tensor is the wrong signature. We also need the game state too, because the policy only makes sense in the context of the game state. Like we need the coin positions. Let's actually look at the usage of convert policy to tensor. Convert policy to tensor MC. Wait, convert policy to tensor in train.ts, right? Train model on the model and examples. Wait, no, sorry, net.ts. Wait, what? Netcf.ts? Ah, yes. So here, convert policy to tensor. We should also pass in the game state. Yeah, exactly. Sorry, okay, forget everything I just said in like the recent future. Well, let's go back into net.ts. So what I'm saying, my argument, which I'm going to say, is like, we have to change the signature. We also need to pass in the game state. Oops. So let me just like make sure that this does not compile. Exactly. We only pass in the policy. We don't pass in the game state. So let's add the game state now. I intentionally did that. Perfect. Just like that, right? Example of 0 is the game state. Status. Or else make sure it compiles. Good. Status. Let's just kind of look at our get diff again. Or Claire first. Claire. Get diff. So what do we do here? So we basically kind of like pre-computed the move velocity stuff right now, and then we added we added a stub here which returns everything as all zeros for now, like a policy which says all zeros. Like it's just we just kind of like we're just like pushing in 0 for like the shape, but we're basically kind of like getting the shape. And then we're actually calling train model, but the only difference now is like we're also passing in, there's also like a new wrinkle where we add the game state too, because a policy only makes sense in the context of the game state. Like we need to like find the route, like the coin, like the coordinates of the coins to do it. Like if you so anyway, so like okay, so get status. So this looks all good. Let's just do get add all, get status, and then kind of look at net.ts. So like well, let's kind of look at like kind of like this logic right here. When we're getting the policy from the game state, like we kind of discretize the game state and like to convert it into whatever, like convert it into to game state model input, which actually like kind of discretizes it for us. And that calls like the get coordinates. Like the crucial discretization function is this one right here, get discretized coordinates. So we're going to use that again. So what this does here, right, is like when we're actually like kind of like taking the policy data, like we have the policy data, like the raw like prediction results, the list of 2400, which we're trying to generate right now, right? We're trying to generate this policy data, which is like a list of 2400 things. But those 2400 things, like we have to like iterate over the coins, and from the coins we have to like get the coordinates and like use those. Like given a coin, like given the coin coordinates which specify the row and the column index and the move ID, the move direction of 0 to 7, these two things, the coin coordinates and the move ID together, specify an index, right? The policy data index, which is like the index in this policy data, like the list of 2400, of which to do. And only the indices that correspond to coins actually matter. And then everything else should be zeroed out, right? Like everything else is illegal. It's like in Connect 4, like the column is completely full, right? So like you can that's probability in the policy should always be 0. I mean, in theory, like as we do more iterations, like they could be filled with junk, but like as we like kind of like do more and more, they should only be non-zeros. All the illegal ones should be kind of all 0 already. Like it doesn't make sense to like in Connect 4 to drop a coin in a column that's already full, right? Then the neural network should output 0 for that column. Like only certain ones are relevant, and the relevant slots in like we have a list of like 2400 elements, the policy data, and the only slots that matter are those that correspond to the coins coordinates and then moves, right? So you have to kind of like do some similar code. So we can actually copy this. So let's just like kind of straight up copy that. Go back down a bit, and let's actually like kind of yeah. So let's kind of finish this, right? Because I have to use a restroom. I'm just going to quickly finish this and end the stream. Okay, so for each coin, what do we do, right? We get the coordinates. We only have to do that once for all the moves. And then move velocity is, okay, so then we do not need the move velocity anymore. Okay, so what do we have? We have the policy, right? We have to iterate over the policy. So for each coin, we can then iterate over the moves and probabilities. So I'm just going to delete these two lines. So now, like for rather than this, what we're going to have here, because like the move and prob of the policies, moves and probabilities, like these basically are the same thing as that. So like let's kind of delete those. And comment this off. So okay, so now we have a move and a probability, right? So that's why we needed the move ID, right? That's the whole point of the move ID. So then let move ID string equals to move and prob of 0 dot move ID, and then let the let prob number equal the move and prob of 1. And then we're going to do some code, like some stuff, and we're finally going to do like policy data of like this. But then rather than this, we're going to have like something called the what do you call it? The policy data index. Equal to the prob. Actually, that's fine. That's fine. Move ID is that, right? Oh no, move ID is a number, right? It's actually a number between 0 and 7, right? So policy data index, to verify this, okay. Policy data index is this. So is the move ID times the number of rows times the number of columns. So that gives you the offset in terms of like the chunks of 300. Because like this thing is a 300 thing. We talked about this already. 8 times 300 is 24. So like each direction, we have like a capacity. Each direction has like 300 things. The 0th direction would be the first 300. The first direction, which is 45 degrees, would be the 300 to 599, right? Like 0 to 300, where it's 0 to 299, and 300 to 599. That's 600 to 99 to what's 600? Wait, sorry, 600 plus 300 is 900. So 600 to 899, 900 to 1200 minus 1, and so forth, right? Like start inclusive, end exclusive. Batches of 300, right? So we have that. So this goes to the offset, and then the row index, which is r, right? Like this coordinates of coin are in terms of r comma c. It's a bit counterintuitive. It's like r is like negative y, right? Kind of. So it's like a bit different. Instead of x comma y, it's more like y comma x or negative. It's in the y comma x format. It's row index, column index. So when we take the coin's row index, we multiply that by the number of columns, because each column, how many like entries does each, like, so row index is like the number of rows you have to kind of skip down, like the offset from that. How many rows do you have to go past, right? So that's the number of rows, and how many like kind of entries do we skip? Like what's the capacity, the size of each rows? Well, each row's kind of length size is 20, which is the number of columns. That's why you have to multiply that to skip past all of them. And then we reach the actual row we're in. And then how far deep do we have to go inside that? Well, that's just a column index, right? It's a consequence of row indexing, like all offsets being measured from 0, which is why all this works. Kind of like a counting number system, right? Extra space, let's just delete that. Okay, so that's good. So we have the policy data index. I think that's it. I think we're now done. Just like that. So I think this looks good. But again, I'm gonna just use Restroom. I'll just end the stream right now a bit early, but yeah, I guess that seems to be good. I'll look at this more, and then we can actually look at the scratchpad file, and actually like play around with this. But in theory, if everything is done correctly, then all we have to do now is just start finish symmetries, and once symmetries are finished, then we just actually run this and then train our neural network. One thing I'm thinking of doing is maybe like kind of outputting a replay file too, so I can actually watch the replays of the bot learning. But maybe I can do that a bit later. Like I have to look at train.ts a bit first. But yeah, for now, in theory, once we finish symmetries, everything is done. Like we're finished. We can actually run alpha zero training and like see how long it takes to see if it's tractable or not. But yeah, like all we have to do now is do symmetries, and I think I'm more or less done. So okay, let's kind of quit that. Get status. Let me make sure it compiles. If it does, I'll add that too. Okay, good. It compiles. Get add all. And then for now, I'll just end the stream here.